Hello, this is A Squared at mathandstuff.com. This video is about limits, derivatives, antiderivatives, the fundamental theorem of calculus, part 1 and part 2. It's presented using a Sketchpad, which makes it dynamic and analytic. Down at the bottom of the page is a link for the videos. We're taking that link. We're passing other stuff you might want to look at and going directly to today's presentation. No date given, it's on the web only. This is the page. The links that are provided are for the Sketchpad itself, a PDF of this page, which you might want to download and write on while you listen to the presentation. You might not want to use it at all. It's available. The video of the talk is here. The teacher's manual, full-blown version of using this Sketchpad is through this link. But we have below the talk for today the abbreviated version of the teacher's manual. What's important to know is this Sketchpad does not present an algebraic approach or a computational approach for dealing with the content. It does not take a derivative, it fakes it. It uses the slope of the secant, very close to the point of discussion. It does not integrate. All it does is plot the sum of the Reimann boxes to produce the curve. We're going to begin now, and I have already downloaded my version of the Sketchpad, and I've saved it under a different name, but this is what's stored on the page. We're skipping the table of contents. We're going directly to limit. I consider limit a background material that some students forget but really need when they're taking a derivative. So with this little button, I can approach. I can approach from above. Let's say we were going to 12. Now 12 is the function's continuous at 12. So we know what the function value is going to be. But as you come from above, you approach, or as you come from below, you approach. There's not a problem with the continuous function. With a non-continuous function, this one has a vertical asymptote. As you approach from above, the function value gets infinitely negative. As you approach from below, infinitely positive. You can clearly see that. The other thing you'd like to approach is infinity. You can see it's pretty stable at 2. Right there's the 2. Next page I'd like to talk about is the limits as x go to. This is the traditional way of presenting a derivative as the limit of the difference quotient. Here is your delta x if you're my age, your H now, and you wish to make H approach 0, the limit as H goes to 0. So we're going to make H smaller and smaller and smaller and smaller and smaller. H is approaching 0. We're still pretty big. H is approaching 0. The curve is looking more like a tangent and less like a secant. We get close. There's your tangent as best we can do it. So the derivative as best we can write it is 27.68. Now we could have chosen a different X value. Let's put the X value there. Let's approach. So you first set where you want it to take the limit, then you take the limit. Next page. This page has something I created, I guess, 2 years ago. These are emojis. I'm looking at this curve. It's a sine curve. The line is a tangent line, but what's of value here is how nicely and quickly it takes the tangent. You can see that the tangent here is 0, so I'm going to use the derivative, and I'm going to say the derivative there is not changing. I go a little bit this way. Now I can see I have a negative slope. Here I still have a negative. Here I have another 0. Here I have a positive. That's all the emojis are meant to do, is document what's being done on the page. You can find the values of the function are listed here. So here's the value of X. We'll call it a constant C. And here's how the function and its derivative are changing. There, the slope is negative, but the concavity is also negative. Concavity is negative. It's concave down there. Slide it a little more. Concavity there looks close to 0. Concavity there is 0. That's an inflection point. We continue to slide the curve, the point C, value C. Here we have a slope that's negative and the concavity is positive. So instead of being concave down, it's now concave up. This is a function I use often. You know it very well. Now let's see it presented dynamically. The function is in blue. I'd like to show the first derivative, and that's going to be in green. I have put instructions right on the page because I forget how to do it, and I think it's perfectly legal. You'll find that on all my spreadsheets. Okay, it says turn off, then on. In the display menu, trace. So I'm going to go to display. I'm going to, okay, trace is turned off. I'm going to hit this point green. Display, trace. We're ready to go. Drag the dot on the axis to trace the derivative. And so to use this one, I'm going to drag this one. Now I could slow it down. I don't need to. All I want to point out is that the derivative of the sine is the cosine. And I could have taken it point by point. I chose to just drag it quickly. I want to take the derivative of that. The derivative of that is in purple. I'm going to leave the traces where they are. And I'm going to drag. The derivative of the cosine is the negative sine. I'm going to go to the third derivative. No, third, I'm going to go to the third derivative. Yep. And that's in orange. Let's see if I can drag the orange. And lastly, I want to drag the fourth derivative, and that's in red. And notice the derivative, the fourth derivative of the sine is the sine. Here's the memory trick. To take the derivative of sine, you get the cosine, clockwise rotation. Derivative of the cosine is the negative sine, and so on. If you want to take the antiderivative of the cosine is the sine, and so on. So I can get rid of that memory trick if I wish. Derivative functions, teaching activities. Enough of this, you've gotten the idea. Now we've played with derivatives. Now we're going to think Reimann boxes, antiderivatives. The first thing you do before taking an antiderivative is you have to partition the plane. Now, there are entire sketchpads on limits. There's an entire sketchpad on Riemann sums. This is just a piece of what you'll find in the Reimann sketchpad. I can take and isolate an area under the curve. I've isolated this one into 4 separate boxes. I partitioned the plane. I built a rectangle with either a left-hand height or a right-hand height. In this case, I have the area of the left-hand box. That means I'm using that height. I'm going to hide the boxes so that all you see is the partition. I'm going to show you the boxes again. All you have to do is click on the link. Here's the left-hand sums. I've hidden them. That's the computation I did for the area of the boxes. And I could go right to the Geometry Sketchpad for Reimann. I don't need that one. I'm going to close it. We're finished with this page. I'm going to on to Reimann sums. Here's a little bit of history. That's what Reimann looked like. Here's a picture of finding a Reimann sum using 4 partitions. Each of them is 2 wide. The difference between B and A divided by the number of partitions. That'll give us our delta X. Our delta X is the length of the base, the function value, whether we choose right, left, midpoint, trapezoidal, the function height. In this case, I used the right hand height. The right hand height. In each case, the height times the width will give you the area of the box, the rectangle. If you add up the areas, you'll get the sum. There are notes on that, and again, you went to the Sketchpad for it. Here's one with 8. Next one. Here's one on which you can input your own A and B in limits of integration. Here's what it would look like if you were using the probability distribution. And I'm going to change, let's make A -2. Let's make B 2. Now you see the whole curve from a value of -2 to a B value of -2. From -2 to 2 should be 34 twice, 13.6 twice, gave you a probability of 0.95. The point in doing this one, I wanted to show you this one to start with, because you could see that if you upped the number of partitions, then it really looks dense. And this is only 32 partitions. 32, that's it. Up it more, we get to calculus. Another idea here is that this is cumulative. We leave out that word in calculus, and we shouldn't, because what we're looking at to take an antiderivative, to integrate something, is to take the cumulative distribution. The people responsible to a great degree for what we're teaching today are Leibniz and Newton for their discovery of calculus. But this page is to show you how A summation which is finite becomes a definite integral which is infinite. How do they relate? The limit of the sum as x goes to infinity is the definite integral. The limit of the sum. How does the finite go to the infinite? Well, let's make this bigger. As n goes to infinity, there's n going to infinity. We take a sum and turn it into an integration. We go from the finite to the infinite as the difference between b and a from a to b minus a divided by n, as that difference, that delta x goes to infinite, it goes to 0, gets smaller and smaller and smaller. The rectangles, the boxes turn to lines. So instead of seeing this picture of boxes, this picture of boxes, this picture looks like lines. That's how it happens. Let's get rid of that. Let's get rid of that. Fundamental theorem of calculus. I'm not even going to bother it. You can read it. I think you know it. Deals with the fact, that, let's make it bigger. And let's just move this. Taking an antiderivative undoes taking the derivative. Taking a derivative undoes taking the antiderivative. We're going to look at taking an antiderivative undoes taking a derivative. So if you started with a derivative, you could get an antiderivative. Capital F of x, that's the function whose derivative you had taken and were given, is the cumulative effect of f of x from a to b. You want the integral from a to b of f of x dx, and it's f of a minus f of b. That's what we're going to use, that idea, as we take an integral. I've plotted an antiderivative here. Here's a function, 2x, linear function. Its antiderivative should be 2x. X goes up 1 power, then you divide by the power with which you raised it. So you're going to get x squared. Well, that curve has the shape of an x squared, but it doesn't line up with what we need because we're off by a constant of integration, y the plus c. Let's make this bigger. What we're starting with is a function whose derivative is 2x. We can't tell what that function was because we can't see if it's the blue one, the red one, or the black one, because each of these has exactly the same derivative, the same curvature. So we need additional information. Additional information. Oh, a constant of integration. Let's make the constant of integration here. Let's make it 0. And now let's make it 6. And what that does is it moves the curve. You knew that. Okay. If the function's not visible, go find the antiderivatives points. Edit a new function and go to the new antiderivatives points. So this permits you to take the antiderivative of whatever function you wish. Let's throw in, let's throw in a sine. And value of the function. Let's take the sine of x. Okay, let's change the grid. We want trig. And now let's spread it out so we can see it. So here's the sine. Its antiderivative is the negative cosine. Here's the cosine, but it's negative now. Let's just make it so we can read it a little better. No, let's change the limit of integration, the constant. Puts it right down where we like it to be. And let's make the limits of integration much closer. Now let's make it negative 3.14. There's our curve. You can clearly see here's the sine function we started with. Here's the plot of its antiderivative, the negative cosine. Almost done. You don't need to just take, or you're not restricted to taking an antiderivative using a base of delta with delta x. You could use a base with delta y. And you can still get the area of integration. That's it, except for some notes. So we don't need the Sketchpad anymore. I think you have an idea of what it's able to do. This is what we went over. The talk ends here, but the reference material continues. This is all available at the Owner's Manual webpage. Last thing to point out is that there are other goodies on the site. The pre-calc goodies are grouped here. The Calc 1 group are grouped here. The Sketchpads are grouped here. And big groups of material are grouped here, and so on. You might be interested in the calc. I have nothing else to share with you. I hope you got something out of the video. Have a good day.